This is example problem number 1 for lab number 1. What you'll need for this construction and other constructions like it is a good sharp pencil or a mechanical pencil with a very fine lead, 0.5 millimeters or so. You'll need a protractor for measuring angles. You'll need a centimeter scale, or in many cases just a scrap piece of paper will serve that purpose, as you'll see in a minute. And you'll need a good eraser, right? So let's take a look at this example problem number 1, and see what we're in for. So it specifies that a plane strikes 020 degrees. I recognize that as an expression of azimuth. It dips 35 degrees toward the southeast. And then typical expressions, that could be expressed as 020, 35 southeast. That's the strike azimuth, the dip, and the dip direction. Or the strike could be expressed in quadrants, such as north 20 east, coupled with the dip and the dip direction. By the right arm rule, it's expressed as 020, 35. And by that notation, it's assumed that if you face in the direction that the strike azimuth is expressed, 020, your right arm points in the direction of the dip. And in fact, if you were to go somewhere and just face 020, that's off to the northeast, your right arm would point to the southeast in the proper direction for the dip of this plane. So the question asks that we find the apparent dip in a vertical section that trends 070 degrees, or north 70 east. The problem is illustrated here in a block diagram. You should recognize that the top surface, defined more or less by the points OAC, this top surface right here, that is the surface of the Earth. And things on that surface will be portrayed in map view in what we're about to construct. And then coupled with that, by virtue of orthographic constructions, we are going to also provide constructions for 2 vertical planes. The one that contains the dip of 35 degrees, and of course that'll be the vertical plane under this line, which is the dip direction. And then another vertical construction, the vertical plane, that underlies the azimuth of interest, 070 degrees. And that will contain the apparent dip that we're trying to find. So let's think about how we're going to do this. And the first thing I've got to do is anticipate a little bit about the way this construction is going to sit on this piece of paper. And right away, I'm thinking we're going to have north parallel to the edge of the piece of paper, something like that, in which case north 20 east is going to be at an angle something like that, again, just estimating at this point. And I'm going to want that strike line to lie right in here somewhere, leaving plenty of room over here for my vertical constructions. And of course, my experience with this tells me that that's the way this is going to have to be. So, my first thing I need to do is to add a north reference line. Because everything, the directions of the strike, 020 degrees, and the trend of the vertical section, 070 degrees, needs to be portrayed in map view. So, to do that, and here's where just a scrap piece of paper will work fine. And I think conveniently, the width of this paper is about the right distance from the edge of the piece of paper. So, I just put 2 little dots. The purpose of those 2 little dots is to guide construction of my line to be perfectly parallel to the edge of the piece of paper. And I prefer this straight edge, it's a better straight edge. So that is going to be right there. All right, so that is my north. There you have it. What I need to do now is to portray the strike of this plane relative to that north arrow. And that's along an azimuth here of 020 degrees. Or in other words, north 20 east, right? And again, that's going to be off in this direction. And I need to decide where I'm going to originate that line on this line. And I'm going to suggest that this is a reasonable position for point O. And that is where that strike line is going to come from. So what I'm going to, having established that, I'm going to put the origin of the protractor right on that spot and align this 0 line along my north arrow. 20 degrees is right there. Okay. And so this is that compass direction. And I think it's just about perfectly positioned. That is the direction 0 to 0 degrees. That is the strike of the plane at the surface of the Earth. That is this line right here. Okay? What I need now, I need to produce this line from O to A. That is in the dip direction. It is perfectly perpendicular to the strike line. And as such, it contains perfectly the dip angle of 35 degrees. So for that one, I'm going to take advantage of, this line at 90 degrees on the protractor. And I'm going to put that right there. And I think that'll do it. That is then, and I'll mark, to remind myself that that is perpendicular, I'll put that symbolism there. That's the dip direction. All right, it is 020 plus 90, so it is 110 degree azimuth. All right, that's rather irrelevant. The important point is that it's perpendicular to my strike. And that is the line OA, so it's O to A. Now we haven't established where A is going to be yet, and we'll get to that. Okay, let's put the dip angle correctly in that construction. Now realize what we're about to do is then the vertical section. It's going to be this lightly shaded plane here, OAB. So what we need to put in here is a 35 degree angle with the origin of the protractor on point O and this 0 line on the surface, right? That's a horizontal line on the surface of the Earth, this line. I'm going to put in a 35 degree dip. 10, 20, 35 degrees right here. 35 degrees. So this is then the dip angle. Now, this angle right here is dip, and I'm in the habit of using this lowercase delta, I guess it is, as symbolism for dip. Fairly common symbol. So that's 35 degrees. And that is actually in a vertical plane. And as such, this is referred to as a fold line. In fact, we can call that fold line number 1. Let's now put the direction of interest for the apparent dip. I'm going to do something a little different than what's shown here. The block diagram shows that line originating at point O. If I do that, I think the lines are going to become kind of mingled and difficult to see. So what I'm about to do is perfectly fine. I am going to put a different point O up here somewhere, just a little bit removed, just to separate these things a little bit. And that is going to be, I guess I'll call it O prime. It is effectively the same as this point O. It's just moved off of the same point for purposes of simplifying the result. So now what I need to do And I guess because I did what I did, I have to do this. I want to produce another north. I suppose there are other ways of doing this, but I want to produce another faint north line going right through my new point so that I can put that compass direction 070 on here rather perfectly. And it only need be a faint line because it's just a little, kind of a little helper line. It does have to be drawn precisely. That'll work. And now I need the compass direction 070 degrees. So the origin of the protractor goes there. That looks fine. 070 is right here. Okay, so this then is that direction. That will be fold line number 2. Okay, up here in the block diagram, that's the second fold line. I guess that is then, you know, fold line number 2, what's labeled down there. And that is this line, that direction of interest, 070 degrees. That is 070. All right. Now, let's think about this a little bit. And I'm gonna come back up to this. Again, this top surface right here, that's the surface of the Earth. The line portraying the dip direction then, on the surface of the Earth, the line OA is right here. If, for instance, this is a large-scale problem and I'm standing here and I'm going to walk out along that line, if I walk out to point A, I will be standing directly above the dipping plane, such that it's a depth D to the dipping plane by virtue of the angle, the dip angle, 35 degrees. If I were to drill a hole right here, and I need to penetrate the dipping plane, I would have to drill a hole this depth, D, to get there. That makes sense. So in this construction that we just put together, that's portrayed here. This is a horizontal line. This is a vertical plane. So all I need to do is establish a point. At this point, sorry for the use of point. Okay. It is truly just an arbitrary point. Let's just let it be here. We'll let that be the point A. Now, keep in mind though, that this is a horizontal line. Depth is measured vertically. So I need to come down vertically from that point to establish the depth D. That then is D. That D is that D. Now, what I just did could have been done anywhere here. And this is where a scrap piece of paper is going to be handy. So what we're saying is that if this is the I'm going to call this length, all right? To be consistent with that notation, that's a length. So that is that length right there. I'm just doing that to distinguish it from depth. I would probably actually call that distance, but that would end up being the same as depth. So anyway, at that length, from the strike line on the surface, out in a direction perpendicular to the strike line, anywhere here, I would have to go down the depth D to get to the dipping plane. So what I'm saying is, and I just did that, this is the length to point A. So I could drill that same hole right there, and I would have to go down the same depth D to get to the dipping surface. I could drill that hole here. Same thing. Most importantly, there is a place on this line portraying the direction of interest, right here, that the same is true. And that point becomes point C. That is point C. All right. What's true of point C, it is one of these points where I have to go down a depth D to get to the dipping surface again. The dipping plane. All right. So let's portray that. And I need to do it vertically. Remember, this is another horizontal line. I'll review that in a second. By the way, as per what I just said, back to this construction. OA is a horizontal line. Depth is measured vertically. That's perpendicular to horizontal. That is a perpendicular set of lines. The same is true here. The line OC here is a horizontal line on the surface. We're considering the surface of the Earth to be horizontal at this point. And that is also vertical then because we're portraying going down a depth. And that depth, you gotta be careful about my marks, that depth is this depth as established here. That is the depth D. I can portray that right here. So what I just established, and I'll come back to this, but what I just established is the point D. That point D is that point D in this construction. Vertically below point C, a depth of D. Wow, that's a mouthful. I hope that made sense. So we're almost done here. And I'm realizing I forgot to label one point, but I'll do that again. We are almost done. This angle then is what I'll tend to call delta prime. That is the apparent dip, solved for graphically. And that angle is, that's 10 degrees, 20 degrees, 25, 27 degrees. That's the answer. What I didn't label back here, and I'll do it now, that point is B. So let's relate this construction to this block diagram again. Again, the strike line here, 0, 2, 0 degrees, is this line. That is a line on the surface of the Earth, so that is map view. All right. This line in the dip direction, OA, of course, is this line, OA. Also a horizontal line on the horizontal surface of the Earth. This line, OC, is of course this line, also a horizontal line, shown in map view. So everything about this is in a map. That map is making reference to this as north. Okay. But these two triangles are vertical. And by what we just did, we just argued that if you go to point A on the surface of the Earth, you would have to drill a hole a depth D to get back to the dipping plane there. And we demonstrated that if you're at point C, which happens to lie on our direction of interest, you would have to go down the same depth D, I should label this D, right, to get to this point, back on the dipping plane. Therefore, a line connecting O, which represents the plane at the surface, to capital D here, which represents the plane at depth, that line portrays the plane in this construction. And this angle then, from horizontal down to that portrayal of the plane, is the apparent dip in the direction 0, 7, 0 degrees. Excellent. So the answer here, the apparent dip in the direction 0, 7, 0 degrees, I'll tell you what. First time I've needed an eraser. We'll just note it this way. Apparent dip equals 27 degrees. Excellent. So I want to revisit this first example problem number 1 for lab 1. And you'll recall in the original construction that we just did, the vertical section, this vertical plane, right, OCD, was constructed over here. And we found the apparent dip of 27 degrees. I want to demonstrate that it really makes no difference. I could have as easily put that triangle over here, and in doing so, I can demonstrate the fold line more perfectly. So let's do that. You'll recall that this is fold line number 2 in the construction. It is this line in the block diagram. And again, before, in the previous construction, we had this line length D from C to D, portraying the depth D, come this way. What we're going to do now is put that line length over here. Now that line, just as it was before, has to be perpendicular. Since it's vertical, depth is vertical, and this fold line is horizontal, that line needs to be perpendicular, of course, to this line. And then I still have, this is depth D, right? This is what we used before for depth D. We can use that again and put it right over here. And so that is at depth D. Let me just make that a little bolder, that part of it. There we have it. And so the only thing left here is to add the dipping plane in this construction. And in this, and I guess to sort of make it make sense, I'm going to turn this over because now it's vertical this way, in which case this is point C and this is point D, and this angle is the apparent dip. And we can go through the exercise of measuring it again just to demonstrate that it'll be the same, of course. It should be. And there it is, 27 degrees. So that worked just fine. Again, what that does is it permits the fold line to be done more straightforwardly. Because all I need to do is fold this along this surface, or this line, and fold this along this line. And I kind of staged this here. Of course, this is looks a little prettier. It was done using a computer, but it is identical to what we just did, right? Here's my, showing the true dip. The trace of the dipping plane is shown there. Here's the other trace of the dipping plane shown in this triangle. And that triangle is, in fact, over on that side of my fold line. Again, what this permits me to do is to what I really want to do is fold that. Right? And this, I think this will all make sense in a minute. Okay, and I will just, I'll turn this to north again. I hope you can see that. I'm not quite sure how it's showing up in the camera. Like I say, I hope you can see that. I will move the camera in a minute. North is still straight up here. And there you have it. I have my little, my little person. And I am going to show a different perspective of this. So there is essentially the map view, okay, what we just did. And I have folded the model along the fold lines to produce essentially a three-dimensional model, right? So here's the vertical plane showing my little Lego person standing above our line segment AB, I suppose. And it demonstrates that, in fact, the dipping plane is at a depth D below her feet. And then I'm going to show you the other vertical plane showing the apparent dip, again, below the little Lego person. At a depth D below her feet, there is the trace of the dipping plane. And the apparent dip of 27 degrees